All right, grind 75 in C++. Let's do 3 sub next. Giggity. Given an integer array nums, return all the triplets such that their indices are different and their sum is 0. Notice that the solution must not contain duplicate triplets. All right, so let's talk about a general approach. So in 2sum, we had an unsorted array, and we iterated through it, and we used a factor of n space complexity to remember the values we've seen before and what their locations were. On here, it's going to be a little trickier. So our target runtime is going to be O of n squared, and it relies on the array being sorted. So if we were to do like a brute force search on an unsorted array, that would be O of n, that would be cubic, so O of n cubed. If we sort it and we only needed one triplet, then we could get away with probably n log n for sorting, plus another n, probably a second n log n for iterating through and then doing a binary search on each step of the iteration. But since we need all of the triplets, it's going to be cubic. The general approach is going to be we'll have a 2-layer nested for loop. The outer layer is just a linear iteration of this index I. On the second loop, each time we change I, it's going to be a 2-pointer approach, changing either j or k until the 2 meet. So that's going to be a linear time there. And so the total will be n log n, which dominates the sorting step, which is n log n. Wait, the nested loop is n squared, which dominates. And since we're past an array by reference, we don't need to necessarily do any sort of edge case checking. Let's start with some of the basics. So we need a return value. So that's going to be a vector of vectors. So in some languages like Python, you might see solutions where they use a hash set in order to check for duplicates. That's actually going to be a tricky part for a C++. The kind of optimal solution, I think, is kind of messy. I don't like it. It's not elegant, but the optimal way actually doesn't even use like a hash set. So in C++, if you were to use a hash set, it's called unordered set. That's the header you would import. And you specifically want the unordered one because then it uses hashing, basically. But then you start having like tricky things like, vectors are dynamic, so you can't really hash them. So you need probably like an actual array type that's set to a size of 3, and you need something that's unalterable, immutable, that's the word. It needs to be immutable in order to be hashable. So like in Python, you would use a tuple. But realistically, the optimal solution doesn't mess with hashing at all. You check for in the loop bounding. So ret for return ret. So that's our basic. And then I'll make the outer loop. So for int I equals 0, I is less than nums.size. And since in the inner loop we're going to have j and k as well, that means we want to reserve those last 2 elements for j and k. I is never going to touch them, because so we're going to have less than extra character. I is less than, so nums.size would be if you want to cover the whole array, -1 if you want to leave off the last element, -2 if you want to leave off the last 2 elements. And then this last section of the for loop would be for how we'd update the variables. It's something you do at the end. So we're going to leave that blank, and I'm going to do it as a first step inside the loop. It'd be a little easier to read. The effect is almost kind of the same, sort of. So what do we need? Oh, we need a sum thing, so I'm going to declare another temporary variable. And it's going to be loop scope, you can declare it outside too, but here it'll the memory will get reclaimed when the loop ends, and we only need it inside anyway. So I'm just declaring this integer s. It doesn't need to start with a value sum of 0, but because we're going to give it a value anyway. But I don't know, doesn't super matter. So if actually we don't need anything there. So let's do the second layer loop. So for int j equals I plus 1, because that's going to be our left-hand pointer that we're incrementing. And then we're going to have another one, k, which is always going to start on the right-hand side, and that's going to iterate leftward. Nums.size. And it's going to start at I minus 1 because of 0 indexing. And it's going to continue as long as j is less than k. We don't want them to meet because we don't want, if they met, that would be a duplicate anyway, so we wouldn't want to use that. And then, okay, actually no, here, sorry, I was getting ahead of myself. We do want to increment I in this outer loop, and it's this section here where we're not going to do our any sort of updates. That's what we're going to do right here. So here's what we do, balance checking. So while I'm thinking of it, a note about the sorted requirement. So you notice on this example input that is very unsorted, so we do have to add a sorting step, and that's pretty simple. Library call, so sort nums.begin nums end. And I don't know why C++ doesn't let you just write sort nums, or even nums.sort. That would be fine, but it's, whatever. That's the syntax. All right, so we've got the sorting step. Okay, so, and notice I'm not going to do anything yet about making sure there's no duplicates. I'm going to do that at the end, because I think it makes the code pretty ugly, so but it is going to be necessary, but I'll do it first such that it would add duplicates. So checking for bounds. So we're going to have this s, so we need to give it a value now, because now we're going to adjust either j or k based on the value of the sum. So s equals nums I plus nums j plus nums k. If s is less than 0, then we're going to increment j. Else if s is greater than 0, we're going to decrement k. And if it's equal to 0, this is where we add the result to our output. So I'm going to try a syntax I haven't tried before. Instead of having like a temporary variable here or some temporary vector and then pushing it onto, I'm going to see if I can use like curly braces instead. If that throws a syntax error, then I'll add a temporary variable. If they're equal to 0, then we want to add it to our output. So ret.pushback. And it's going to be an array of nums I, nums j, and nums k. We'll see if that throws any errors. I'll just check for that now. It's going to be an incorrect result, but I'm just seeing what it does for errors. Oh, you know what? I forgot. So in this step also, we do need to either adjust j or k. It actually doesn't matter. It's totally correct to do either one. I'll just adjust j, I guess. But I have tried it with both, and it totally works. Okay, so output. Okay, cool. This syntax is working. Instead of creating like a temporary vector, just put in curly braces and it figures it out. So in that case, yeah, so see what I was saying about duplicates? That one, okay. So I'll do duplicates and then I'll talk about runtime, do a step through a mental example, and then we'll submit. So duplicates. our array is sorted. That means whenever we have the same number twice, they're going to be adjacent. So here, I'll write out an example. So we have this example here. This is our input. And after we sort it, it becomes minus 4, 4, minus 1, minus 1, 0, 1, and 2. So this is our sorted. So we've got these. So basically, whenever we update any of the three indices, I, J, or K, we want to just keep going until it hits a new value that's different. And then we want to do some, since we're looking at like adjacent indices, we do want to do some bounds checking to make sure we're not going outside of bounds and looking at an illegal index, which will throw an error. So let's do that here. So if I is greater than 0, so it's not the first index, and nums I is equal to nums I minus 1, because it's going from left to right, so we'll look at the previous one. And we're just going to continue because it's going to iterate anyway. Did I spell that right? Why is it yellow? C-O-N-T-I-N-U-E. Okay, well, whatever. And then similarly, we want to do something like that here. So there's a couple of places we could do it. We could do an if condition here. We could tack it onto this if condition. Actually, that's kind of what we have to do anyway, because we want to do something based on. So if j is the same as, if the value at j is the same as before, we want to keep. So I'm gonna throw it into this these if conditions, even though it's after where this s is calculated, because it adds the minimal amount of mess that I can think of. It's ugly. I am not a fan. So if s is less than 0, or because we want to ignore duplicates, I is greater. Wait, no, not I. J is greater than I plus 1, so it's not the first value of j, and j is greater than I plus 1, and j is the so nums j equals nums j minus 1. All right, so let's think about precedence and if I need to add parentheses to this. So and is pretty strong, so that's going to be there. I think or is kind of weak, so it may bind these first and then do equals. And then or is kind of weaker too. So I'll try it without, and then if I need to add parentheses, then maybe I'll have to add parentheses. But I do have to think about the order of precedence and like, does the grouping work without them? When in doubt, you can add more parentheses, but it's also, you know, a good place to show off knowledge of order of precedence for the language. So, and then we're looking at k here. So if k is less than its first value, which is nums.size minus 1, and nums k is equal to nums k plus 1, because that would be our previous value for k. Okay, and then, so that's if either of these two are an issue. All right, so we've got I here, and then it'll just continue, meaning it'll increment I again. We've got J here, meaning if it's, you know, not the correct value, or if J is going to give us a duplicate. Because realistically, we only need to look at one of them, so we'll just look at the first copy of each value that j is going to hit. And then same with k, if it's greater than 0, or it's going to, yeah, so in this case, we'll look at the rightmost copy of whatever k is going to give us. And then hopefully that doesn't mean that looking at the first value that j gives us and the leftmost for j, rightmost for k, hopefully those don't clash before j becomes equal to or greater than k, and we break from our loop. So I think that's it. Let's step through an example. All right, so we've got this one here, and we've sorted it. So what do we do now? So we've got I. We're going to initialize it. So so I starts at 0. And then we're going to check. Well, this is going to skip. So I is 0. So we're going to skip this. J is going to become 0 plus 1, which is 2. Sorry, 1, index 1. So minus 1. So 4 minus 1, and then K is going to be. While I'm thinking about it, sometimes it can be. If you're looking to like absolutely squeeze the most juice out of your runtime, you can have like micro optimizations that like really, you probably don't want to do this in an interview setting, but it's just something to think about if you're like doing an embedded device and you need like every last bit of performance. Calling something like nums.size on every iteration of a loop, that's less optimal than say declaring a variable, getting the size value front, and then using it there, because the size is a method. It's going to have that little bit of overhead for access. As opposed to just having a local variable and then reusing that over and over again. And that'll be something the compiler can optimize more easily, because then it'll know it's only going to be set once and it never changes, as opposed to, well, maybe it's going to be harder to reason about knowing if this size is ever going to change during runtime if you use the method instead. Okay, so back to the example. We've got I, j, and then k is size minus 1, so it's the last value, so 2. Our sum here is minus 5, minus 4, minus 3. All right, so sum is going to be minus 3. That is less than 0, so it's going to hit this condition. It's an OR, so it's going to ignore everything after this first thing comes true. So j is going to increment. So now we have I, j, k. And so this time, it's still going to be less than 0. So even though it's a duplicate, we're never going to check this part. But it doesn't matter, we're going to increment. So 4, 0, 2, so that's going to be minus 2. That is still less than 0. Okay, so we're going to increment j again, still same condition. 4 minus 4, 1, 2, that's going to be minus 1. Still less than 0. Next iteration, j is going to be equal to k, so I have nothing on that iteration of the outer loop. All right, so I becomes 1 now. So we're going to have minus 1, and then check this condition. I is now 1, so this is going to be true. Is the value at 1 equal to the value at 0? It is not. So we do not hit that. We keep going. So we have I, j is now I plus 1, so j, k. So that's minus 1, and 2. That is equal to 0. So what happens then? We check this. J is not the first value. Actually, no, it is. J is the first value, so that's not going to trigger. It's not going to be greater than 0. K is also equal to its first value, so this isn't going to trigger. So we hit here. Pushback, minus 1, and 2. Is that what we want? Oh, okay, good. That looks good so far. And then here we increment j. Again, maybe at the end I'll try submitting with both incrementing j and decrementing k, just to show you it really doesn't matter. All right, so next iteration, increment j. So we have I, j, and k. Well, that's minus 1, 0. Okay, so that's the sum is 1. So what's going to happen? This is false, or this is true, and this is not true, because we have minus 1 and 0. Wait. No, increment, yeah, minus 1 and 0. So that is not true. So then we check the next condition. S is greater than 0. That is true. So then we're not going to look at the rest of this. Or actually, no. So that, wait, sorry. Yes, that is true. So we're going to decrement k. So k, instead of 2, becomes 1. So we have -1, 0, and 1. And just, we'll keep reasoning through this, but this is going to be an example we want to be added to our output. So we decremented k, so we're up here. Sum becomes 0. This is not true. Is this a duplicate? Well, -1 and this is I, so our j is at 0, so that's not going to be equal to I. So this is true, but this is not true. J, this is not true. This is true. This is not true because it's 1 versus 2. All right, so that's not going to hit either. So we hit the else condition, and we add it to our output. And then we increment j. So now instead of 1, 0, 1, we have 0. So j and k are now both here. That's going to be our exit condition for this part of the loop. So then we go to the next iteration of the outer loop. So instead of 1, so now I, this is our, so I think I is here now. So 0. This is not going to be true because it's 0 and -1 that it's comparing. So this is true, but this is not. So now we're at 0, 1, and 2, last iteration. 0, 1, 2. Sum is 3. So that's going to be greater than 0. So that's false. This is false. So then it does not check this. This is true. This is false, so it's not going to check this. And then we want it to pass through. So there's no, wait, no. I'm sorry. It's greater than 0, so it's not going to look at any of this. It's just going to stop it here. S is greater than 0. Decrement k, next iteration of the loop. Well, now k is 1 and j is 1, so that's going to exit our inner loop. That was the last step of our outer loop because we're excluding the last 2 steps. And then we break, return, we're done. So we did add those 2 outputs. There wasn't a third one. I probably should have wrote them down, but we did see that it matches there. These 2 look like edge cases. So I'll go through one of them. So let's do example number 2. 0, 1, 1. Well, it's already sorted order, but we're going to sort it anyway. All right. First and only iteration, I equals 0. J is 0 plus 1 is 1. K is 3 minus 1, so 2. I, J, K. Well, their sum, so first check here. I is greater than 0. It is not, so we skip that. Here, sum is 2. It is going to be less than 0, so that's false. So now we check this. This is false, so we don't check this. So now S is greater than 0. This is true, so we skip the rest of this. We're going to decrement K. K is now here, and K and J are both here at this middle index. And then that's our break condition, so we exit, return, we have an empty output. Yeah, all right. So the runtime, we have n log n, O of n log n, I'm going to use O of n log n for the sorting step. Now most, probably some libraries are going to use, all right, so the gold standard of comparison-based sorting is going to be merge sort. Merge sort is theoretical upper bound n log n. It might be more common for a standard library to use something like quicksort, which is going to have a little bit of a faster average runtime at the cost of potentially being O of n squared in the worst case. For here, I'm going to assume O of n log n without digging into the implementation details. If it's merge sort, it would be n log n. If it's quick sort, which is probably the other most popular choice, there's like dozens of sorting algorithms, but those are the two most common ones. Just keep that in mind. Quick sort is actually O of n squared. Worst case, but a little bit faster, average case. All right, so we've got O of n log n sorting step plus, and then we have this outer loop, which is O of n, and then an inner loop, which is the two-pointer approach, which is another O of n, because we do a constant, all of the operations we do inside of it are a constant time. This is always 3 in length, so it's all constant operations, so it's O of n squared, nested loop, which dominates. O of n squared total runtime. And now the space complexity. Since we're doing this iterative, like checking and incrementing our pointers, it is going to be constant space if you're excluding the output. Now the output could be potentially, well, since there's no duplicates, then it would probably be O of n if you count the output, or constant if you don't count the output. Space excluding. If there were, say, no duplicates, sorry, if duplicates were allowed, you could maybe potentially end up with a cubic space complexity for the output, but you can't reduce the size of the output. That would be changing the function parameters. And yeah, it's mainly correct because it's kind of it still feels kind of brutish. The only thing that's not brute force about it is this inner loop, which does two-pointer, and it counts on it being sorted in order to achieve that. So that's sort of the correctness. Let's give it a whirl. Let's give it a run. What'd I miss? Nums. Oh, nums with an S. Typo. All right, accepted. Yeah, and so just to reiterate, I didn't do any like edge case checking for like an empty input. It might hit some errors well, actually no. So if nums was less than 3 in size, then pretty much, you're going to initialize J and K, and immediately they're going to be equal, or J would even be higher immediately. So then this inner loop will never iterate. I will just step through, nothing will happen, the return value will never get populated, and you return an empty vector of vectors. So let's click it, submit. Cool. All right, so that was threesome. We will mark it off our list, our bucket list, and we're done. Thanks.